We had the other observation, which was what? The friction's getting larger as we tilt an incline. So we can see that, right? If I tilt the incline, the greater amount. What happened to the acceleration? Bigger. Okay, so that shows us that it indeed does get bigger with an increased angle. Good. But yet, the calculator was still at rest. So we can bring Newton's first law into analysis, right? And what does Newton's first law tell us? If, so an object at rest remains at rest if, what? What? Thank you. The net force is zero. The total force is zero, right? Boy, we got there somewhere. Okay. Feel like I'm playing slot machine. Okay, so with an incline, we say that F sub G, and we have two components. One is the normal force. We'll oppose this. We'll solve for this later. This is F sub G cosine theta. And this component is F sub G sine theta. Yeah? Okay, so then what happens? As we tilt the incline, we see that F sub G sine theta is getting bigger. That's an observation. The car accelerated at a greater rate. So again, we go back to Newton's first law, which I abbreviate with N1L, which says at rest remains at rest if F, I don't know where this alt G is coming from, F net equals 0. And remember, force is a vector. So we have to do components. What is the force preventing the relative motion between the calculator and the surface? That's right. So we know the force of friction has to oppose the motion. So in the second case, this is bigger than force of friction 1. Because I'm going to have, if I choose my coordinate system this way, I'm going to have F sub G sine theta minus force of friction equals F net equals 0. Everyone follow my logic there? As I tilt the incline, I increase Fg sine theta. So how does friction play a role in keeping it at rest? What must be happening to the force of friction? As theta gets bigger, what happens to the force of friction? It increases. That's right, up to a limit, as you said earlier. Yep. So it had a limit. So if we look at the applied force versus the force of friction, we're going to see two behaviors in our ideal model, okay? We're going to see a 1-for-1, 45 degrees. The force of friction equals the applied force in magnitude. So they add up to 0. All the way up to some limit where it fails. That's called the static limit. And our straightforward assumption is once it begins to move, we enter a regime we call kinetic. So we're going to differentiate between kinetic, moving, and static. So do you see how the subscripts help us remember which one we're dealing with? Okay. So when we write down in our idealized model, we're going to say that if something's sliding across a surface, the force of friction is a constant value, approximately. But if it's at rest, this one-to-one mapping says what? This is less than or equal to mu sub, S, F sub n. You see the less than or equal to? It's as big as it needs to be to keep the surfaces at rest. No bigger, no smaller. Up to that limit of the equality. Do you see the little line underneath the arrow to the left? Less than or equal to. So in a problem, when there's friction involved, and the problem says like when it just begins to move or it's about to move, that's telling you we're at that static limit. Okay? And it will move after that, won't it? It will accelerate after it breaks free because the force of friction drops. It becomes less in the kinetic case. So it will decrease the force of friction, and so we will have acceleration. Yum, yum. In our model, in our understanding of what's going on, is it okay if I use these white spaces to do some more notes? Okay. In our model, it turns out that even the smoothest surface has some irregularities on it. The irregularities might be a single atom step, or more likely they're bumps on the order of micrometers or tenths of micrometers. And because they're two different substances, they will have different electronic behaviors. But as we discussed with the normal force, we assume that to a large degree the surfaces remain whole. What is purple remains purple. What is red remains red. Okay? Nothing rubs off. But if you notice, what's going to happen when these irregular surfaces engage each other? We're going to develop what? We're going to have this contact that says, you've got to get past me. So either we have to bend, we have to rearrange where the atoms are that are in the protrusion, or we actually have to lift up the block, and all that requires a force. So static friction says, great, we have irregularities, and because we're friends and we have charges, we also have some bonding that goes on in the dark between the two surfaces. You got an electron here, you got an electron there. They like to play games. chemical bonding. So these two forces, or these two interactions, oppose motion between the two surfaces. Again, I stress a relative motion. Relative motion. One relative to the other. Yum, yum? Cool. And so what happens when we reach that limit? When the upper surface begins to move, when the purple block begins to slide, what happens then? Do we still have irregularities? Do we still have some bonding occasionally? But they don't fit together as well, do they? Because they're moving past each other. Yeah? I mean, think about it. Have you ever, for example, tried to move a heavy box, cardboard box, a desk, a cabinet perhaps, across the floor, and you push and you push and you push, and it won't move? But some of you, like myself, who really don't care about personal injury, will do one more thing before we give up. What is that one more thing? You can lift up, that's good, reduces the normal force, or what do they call it in hockey? Give it a hip check. So you give a brief impulse, extra force to that object by throwing your body into it sacrificially. So that briefly raises the force that you're pushing with. And if you're lucky, if it's within the range of not breaking your pelvic bone, you will exceed the static limit of friction, and then what happens? The box will slide. But do you still have to keep hip checking it the whole time? No. Generally, not always, when the box begins to slide, the friction force decreases to where your push is enough to keep it sliding. Try that on some tables during our break if you want to. Okay? Everybody with me on that? So relate it to your experiences. Take a calculator, push on it with your finger. You push gently and a little bit more and a little bit more and a little bit more, and it breaks free, and then you keep it moving without accelerating if you get your finger with a force equal to the force of kinetic friction. Yum, yum? Now, mu, these mu's, mu sub s and mu sub k, mu sub s and mu sub k are called coefficients of friction. Their values depend on the types of surfaces. For example, wood on sandpaper versus, say, Teflon on, I don't know, a waxed floor. Anybody ever sanded wooden blocks? If you push them together, it can be very, very difficult to get the sandpaper to move. In fact, within your hands, you develop a feel for if it doesn't move, quit pushing as hard into the block. But once you get it moving, you can reduce the force and get it to move smoothly. But suppose I take one of your Tefal, or whatever they're called, cooking pans or something that have Teflon on them. Is Teflon rough or is it slippery? It's slippery. So we expect that Teflon on a waxed floor to be very low coefficients of friction. In our model, where there is integrity between the surfaces, the bonding between the surfaces is not too large. That is, we're not talking about Scotch tape or dragster wheels or tires that have been heated up before a race. We're going to find that mu is generally less than 1. Certainly exists greater than 1, but we're going to deal with a simple limit. If you want more details, there's a magazine that comes out periodically on tribology, on the friction. That's why, for example, you add oil to your engine. You've got metal parts moving past each other. At high temperatures, at the combustion temperatures, those metal parts will fuse with each other. That is, the static friction just takes over. Those bonds get made, and what have you done? What's it called? Yeah, you seized your engine, so now it's time to go get a new engine, right? So that's why it's important to keep that lubricant between all metal surfaces. So as an engineer, you're going to have to choose materials to make the surfaces out of. And as an engineer, you're going to have to discover where are the maximum points of forces as an irregular object, maybe called a cam, is rotated about a pivot that's not at the center, and it's rubbing a surface. So one might call that a diesel engine. No. So this edge that protrudes might become your engineering limit. That's where the greatest stress is occurring. That's where we really have to pay attention to what's going on. Yum yum? So when you buy a saw blade at Home Depot to go through lumber like you're building a house, what do you observe about the saw blade? What are you going to buy? I'm going to buy a, 8-inch, 9-inch saw blade. What characteristic does it have? You pay a little bit extra for, but it helps the blade last longer and give a cleaner cut. Number of teeth. Height and shape. Good. Wow, y'all are experienced. And there's one other thing you'll get for general purpose blades. Sometimes, diamond coated for really fine stuff. But for bigger stuff, we have carbide tip. And that's actually, if you look at the blade itself, you will find welded to it little blocks of carbide that extend just beyond the edge of the metal of the blade. They're welded in place. So the cutting surface is actually the edge of the carbide piece. I once had a buckled floor. It was wood, and so it was buckling a couple of feet. The person had forgotten to consider that during the summer with humidity, and this being real wood or bamboo, moisture absorption makes it expand just a little bit. And if the strip cannot release that pressure, so you got it within two walls, and this tries to expand and cannot expand, it relieves that stress by buckling, which makes it awkward to open doors and walk on the floor. But it doesn't have to be that big of a lateral expansion. You get a much bigger hill made out of it. You do the geometry of the whole thing. Okay? You let it acclimate, but even then there's seasonal variations. So what do? Where the wood panel meets the wall, you put a furring strip there, but you leave a gap between the wood and the wall to allow it to expand and shrink. And I don't think they did. They put it up snug tight. So I took a saw blade. I was desperate. I took a saw blade and just cut down along that ridge It doesn't look pretty, but by cutting out enough of the wood, I was able to give it room to expand. Then I filled it with some putty. And people make fun of me for that. It works, so I don't care. I'm a functional kind of guy, not aesthetic. But the problem was, what's it like drilling through wood that's resting on a concrete sub flooring? Oh yeah, I was really pretty darn interested in this. I wanted to get this to work. So I discovered quickly that if I wasn't careful about the depth of the blade, if I set it too deep, that my cutting wasn't going very fast. And what had happened is I'd knocked off the carbide teeth when they hit the concrete. So I was cutting with the nubs left behind of that soft metal. So I was sort of wearing out the wood, which is probably why it smoked. Yeah. But there you go. That's friction. Now we assume that the friction, yes, it opposes the motion. That's an excellent question. Let me follow that up in a couple of minutes. Line calculator slide on a bubble angle versus a shallow angle later on. What can explain the angle of repose for one case being that big and for the other case being roughly that big? It's the same calculator. Not that long. You naughty boy. I flipped it over. It's the surfaces that are in contact that determine the friction properties. So when I had it flipped over one way, I had it resting on those little rubberized buttons, those keys. Whereas on the second case, I had it resting on the hard plastic shell. Sliding plastic, hard plastic, pretty low friction. Rubber, pretty high friction. Yep. So again, as you were pointing out, opposes relative motion. When we look at diagrams of forces and frictions involved, we're going to have to ask ourselves, what's the direction of friction? Sometimes it's going to depend on things like speed or radius of curvature with circular motion. But in the simplest way of looking at it, we do the following. What would be the relative motion of one object on the other if, in my vernacular, as I've used it several times, I put it on roller skates? How would it move if it was on roller skates? How would it move if I removed friction? In this case, it would do what? It'd go down. So which way does friction have to be? It has to go up. So it moves down, right? So that means force of friction would have to be up. Let's take another orientation. Suppose I have a block on a block, and I'm asking about the friction force on the upper block. And let's assume I am accelerating. I'm going to push on the lower block to make the whole system accelerate to the right. On the upper block, what's the direction of the frictional force? Say it loud and say it proud. It would be right. F. Yeah, it's easy to anthropomorphize that. It wants to, but you're right. It tends to. Newton's first law. An object at rest remains at rest. So if I put that upper box on roller skates, I would be pulling the lower box out from underneath it. So do you see that the upper frictional force is in the direction of the acceleration? It's not that friction opposes acceleration. It's that friction opposes the What motion? Relative motion between the surfaces. So again, this is how I think about problems of this nature. Anything involving friction, well, when it moves, when it slides, you know which way it is moving. Okay, you know that the direction's opposite the velocity, right? If V is the speed or velocity between the two surfaces. It's the static one that's a stinker. The static one is a stinker. Because what would happen if I took the lower block and I pushed on it to the left? Exactly. It's always the motion of one surface relative to the other. Okay? In the case that the lower surface is moving, is accelerating, then I can get friction to go in the direction of the acceleration. If the lower surface is fixed, like a floor, then friction always opposes the motion. Always, the motion, not relative motion, opposes the motion. You like to work these problems, wouldn't you? You're exactly right. Yeah. Well, that would be up and down, though. Gravity's pulling it down. So the other thing about friction we notice is the contact force. What do you do to a dresser where you got lots of clothes or lots of other things in the drawers and you want to move it across the floor? You take the drawers out. Why? That reduces the inertia, but it also reduces the weight. So it reduces the force pushing the surfaces together. So it reduces the maximum force of friction. That's why we have, let me choose a nice bright color. That's why we have this factor of the normal force between the surfaces. The more you push two surfaces together, the more you would expect them to nest, the roughness to nest with each other. NASCAR driver, suppose you had a caution flag up for about, 4 laps or 5 laps. Going into the pit, you got more gas, you got brand new tires, and you're on that surface going what looks like 10 miles an hour, but I think you're really going about 60. Okay? What do they tend to do as they're waiting for the race to restart? Yeah, they drive like they're drunk. They go back and forth and back and forth. Why? They want the tires to be hot. And I would imagine for 2 reasons. You want it to be hot because you want to get roughly the pressure you'll have when you begin racing. You want to have a smaller change in the pressure while you're racing. They get very hot. Yeah. So that's one of the critical things that the crew has to determine when you pit. What should be the pressure in your tires? Sometimes left side's different than right side. If you're hugging too much, not going fast, you need to increase the pressure. If you're sliding too much, you need to decrease the pressure to let more contact with the surface. But it also warms up the rubber. So that's something, if you watch, pay attention to it. On the white flag lap, which is the last lap before you open up the race, you see them really going back and forth until they get like the 4th turn or so. Then they straighten out and they're ready to go. Cool stuff? Okay. I don't know about you, but I have many, many unfond memories of erasing errors on pieces of paper as a kid and ripping the page because I had too much of a normal force, which increased the static friction force, which got to the point where I'd shred the paper. So hopefully you've learned by now, A, use a softer eraser, and B, it's better to make 5 erasure movements than one that makes a hole. Y'all can relate or not? I'm not hearing anything. Yum yum or yuck yuck? Okay, cool. So every force is related to one of the 4 fundamentals, as I discussed earlier. The nuclear force and weak force are very, very large. It's a strong one in particular, but it has to do with forces within the nucleus. So it's a very, very small range of a force. That is, you might have the force be huge, up to about 10 to the minus 15 meters, about the size of the average nucleon, proton, or neutron. But when you go to 10 to the minus 14, its strength is much, much smaller. I think it's like 1 over r to the 5th power or something. Now, the electromagnetic and gravitational forces are long-range forces. They go as 1 over the square of the distance. Now, between you and me, 1 over the square versus 1 over the 5th power, you're getting small. But mathematically, it becomes really different. Okay? Also, the nuclear force has other issues as you get further from it. So it disappears quickly. That's why fusion is so darn hard to achieve. You got to get those nuclei right on top of each other. Otherwise, they'll just skip off of each other due to the electrostatic repulsion. Why does the force between charges, like charges repel, opposites attract, why does that not dominate our lives as we walk around the world? It doesn't dominate our lives because, for the most part, we have 0 total charge. We are neutral, roughly. Depends what the weather is and what we're walking on. So no charge doesn't attract other charge. But we do see the electromagnetic force in almost every force we have physically. A rope is made of fibers that are molecules attached to each other by the electromagnetic force. Friction is due to the electromagnetic force between the atoms that are held in place by the electromagnetic force and the bonds between atoms, which are electromagnetic. Okay? Sticky tape, Scotch tape, masking tape. That adhesion is due to the distribution of charges within the sticky stuff. Yeah? How many of y'all realize that Scotch tape has more than one layer on it, or one type of plastic? That is, you know about the sticky layer for Scotch tape, don't you? Right? This is the sticky side. But there's more than one layer to the Scotch tape. There has to be more than one layer of the Scotch tape. Why does it have to be 2 layers? Not so much. Think about Scotch tape when you no, I think it's another plastic. You want the sticky glue to stay on the tape, right? So when you put the tape, it brings the sticky glue with it, right? But when you peel the tape off of the roll, the upper surface doesn't have any glue on it. Well, it's different properties. I don't know if it's conductive or what, but there's something different about how the charges interact. You're exactly right. Because anyone who's an artist or mounted things and you didn't want to see the tape knows that the nastiest type of general use tape that you can use is double-sided tape. And I have no clue as to how they get the glue to stick to the other pieces, but not to the glue. You know what I'm saying? Double-sided tape has adhesive on both sides. And that's hard to work with. But anyhow. So, what is it that drives fusion reactions, the creation of stars, planets? It's gravity. It's that wussy force, right? Again, I said if the gravitational has 1 unit of force, then relative to that, the nuclear force has 10 to the 40th basic forces. That's a lot of zeros. I won't even begin to tell you that. But it's just to relate to it about the size of the atom to the entire universe. But gravity, have I told you about stellar formation? A little bit? Okay. Gravity is what pulls the hydrogen together out of a very, very spread out distribution, clouds of it, if you will. So it accretes, it gathers together due to gravity. And as those pieces fall to each other, they are going to a state of lower energy. Gravity is pulling them in the direction they're moving. So there's less potential energy. So the atoms get hotter and hotter and hotter. And then the gravity makes them closer and closer and closer together. And it's a combination of the hot, which means the nucleus is really moving, and the density, which is how close they are together, that determine if a ball of stuff becomes a star. If it gets dense enough and hot enough, boom, the hydrogen nuclei start to fuse. So I get hydrogen, and they join to form helium. And when that happens, based upon nuclear physics and stuff, it turns out that releases energy. It's exothermic. And that's where you get energy for a fusion reaction. That would be a real nice thing to do because we could take fuel that's hydrogen, which is plentiful on the Earth. There are 2 of them in every molecule of water. And by fusing them, we would make helium. So we could fill lots of birthday balloons. And we would also release the greatest amount of exothermic energy. You are stardust. That's right. Yeah, exactly. If there's a release of energy, release of pressure, then they don't fuse anymore. You can design fission reactors to do the same thing, but those are newer designs. So that's where the moderator, which slows the neutrons so they have a greater chance of being absorbed by the uranium nuclei, that is, it increases the rate of fissioning. You can have a design where if something fails in the control system, rods of boron, that moderator, you can use not only boron, but you can use water. And water is good to use because it has a very high heat capacity and a latent heat. That is, it takes a lot of thermal energy given to water to make its temperature rise. So it's a great transporter of energy. And that's what happens. The water circulates either in 1 loop or 2 loops under high pressure and high temperature. And the water, as it's allowed to expand and form high pressure steam, is what turns the blades of the turbine that makes a generator turn. Okay? If you design the reactor so that in the event of failure, you just let the water drain out, that could make the reactor subcritical and it would shut down automatically. I just put more water in it. It depends on how fast they're cooling down. You're exactly right. You're right. If you come down too quickly, then there's enough thermal energy left to create a problem, which I was given to understand happened in Chernobyl. That is, they ran it hotter than it was rated to. They wanted to see what would happen if you went to 110, sort of like Spinal Tap, wanting to go up to the level of 11 on the knob instead of 10. So they had to disable a lot of safety systems to do that. Not that the Russian reactors have as many as the other reactors do, like containment buildings. Who knew you need those? That is a secondary shell. And so what happened was when the reaction went supercritical, they tried to put those rods of boron back in, or whatever it is. I forget what it, maybe it's, yeah, anyway. They try to insert or let these rods slide back into the holes within the fuel rod assemblies. And because of the temperature increase, they couldn't get them back in. And so they had melted them, distorted them. So now you had no way of shutting the reaction. Yeah. I'm sorry. If that's some kid's idea of a science project in middle school, hopefully the safety review would say, "Yet, no, bad idea." You don't want to take off all the safeties. Okay, so we have other forces. Okay, we have the spring force. What do we have before? We have the normal force. We have the friction force. Whoops. Static. Kinetic. We have the force of gravity near the Earth's surface. Magnitude equals mg. What's its direction? Up, down, left, right. What? It's not up or down. It's towards the center of the Earth, which generally is down. But I just want to let you know why the people in Australia don't fall off the Earth, because their radial direction is down to them. Do you ever wonder that as a kid? Why don't they fall off? Well, because gravity points to the center. Okay. What other kind of forces? We have a force that's associated with a pull of a flexible object. It's called a tension. The characteristics of tension are it's only pulling. It's hard to push a dog on a leash. You can pull them, you can't push them, because the string is flexible, right? This is you going, what? You can't get that dog to go woof by pushing the leash. And the other thing is the direction is along the rope. Why does it have to be along the rope? Because if it wasn't, then the rope would bend until it was. That's what makes mechanical engineering really challenging, where instead of having flexible members like chains or ropes, you have solid objects, and now you can have different directions of the force between them. A compressive force and a shear force, for example. That gets to be real fun in engineering. And there's one other thing. The tension force is constant within the string. No, it's just the magnitude of it. It's constant, assuming that the weight of the string is negligible. So suppose I were to suspend a mass from a string. A string. Haven't gotten there yet. Good. The force of tension of the string on the mass opposes the force of gravity of the Earth on the mass. And those add up to 0 because the object's remaining at rest. I assert that the force down on the ceiling from the string which is equal and opposite to the force of tension of the ceiling on the string, is the same magnitude. Let's look at the string. I have the force of tension of the ceiling on the string, and here I have the force of tension of the of the mass on the string. I didn't draw that one for this case. Force of mass on string. Force of string on mass. I've got that one. Okay. With those two forces, if they were not equal in magnitude, what would that give me? It would give me a net force. And you know that if there's a net force, the string is going to accelerate. But the string's just, pardon the pun, hanging around. So that's why the tension is constant. If it wasn't constant, then one side in a tug-of-war contest would have an automatic advantage over the other side. You want your pull of your team to be equal to the pull that the other team experiences. It'd be nice if it was bigger, but we can't make that happen. Everybody good with tension? And then there's, like you said, force of a spring. So we call that F sub S. And that works out to have a magnitude of K delta X, where delta X is displacement from equilibrium. It's called the spring constant, and it's measured, as we might do this semester, by saying that K is the ratio of the force of the spring to the delta X. We can apply greater and greater forces, which would correspond ideally to greater and greater stretching of the spring or compression, and that would allow us to find K. Now, imagine we have a table, and on the table we have a block and a mass, and let's assume this is where X equals 0, and it stays there. An object remains at rest if the net force on it is 0. This also applies, therefore, to masses hanging from a spring. Okay, we'll get to that later. What happens if I force the mass to move to the left? What does the spring do? Right, it gets smaller. The spring opposes the displacement. That is, the force of the spring is directed opposite to the displacement. If you have a spring, then you have something which tries to bring the end of the spring back to equilibrium. So it's called a restoring force. So if I stretch the spring, what is the force of the spring on the mass? Pull it back to equilibrium. So to write that in a vector form, we can say that F vector of a spring is negative K times delta X, whereas you hopefully will recall, negatives have nothing to do with magnitudes, they only have to do with directions. A negative direction is opposite. Yum yum? Cool. Sometimes F sub n is just called N. Sometimes F sub g is just called mg. Sometimes force of friction is called F, italicized. Sometimes the force of tension is called big T. I don't like that, and I know that I differ, but I can differ because I've used lots of textbooks. And let me explain why I differ. I differ because of two main considerations. If you follow my model, every force will be labeled as F. F stands for force. The subscript tells you what kind of force. Contact, weight, friction, tension, whatever. By having to memorize these individual letters, it's easy to get confused. For example, N can represent in vector form the normal force, but in plane form, it's the unit known as Newton. T is also the symbol for period. F is also the symbol for frequency. Okay, you got me on the mg thing. Okay, so I'll use mg sometimes. I'll slip it in really quickly. So that's why I would like for you to use Dr. McNary's special way of doing things. I think it reduces confusion. Okay, so think that over. You have to translate that on diagrams that the book gives you to make sure you understand a problem. We've talked about inertial frames of reference as applied to Newton's first law. That is, when I look at something happening in your frame of reference, I will agree that the laws of physics are working out pretty well, as long as I am not accelerating relative to you. That is, I'm not going faster relative to you. My speed's not increasing or decreasing. My direction is constant. If I'm in an inertial frame of reference, physics works. So we say Newton's first law applies to all inertial reference frames. You know? I showed you by throwing something up. Did I not last time? Right? When I throw something up, within my frame of reference, I see the ball go what? Up and down. If I do that with you, and I'm at rest, we see the same thing, don't we? And we're like, yay, physics. But when I walk across the floor at a constant velocity, I see what I saw before. You see a parabola. I'm pretty happy with the physics. You're pretty happy with the physics. That's what it means to say inertial reference frames are equivalent. Just like if you sit in the corner of the room in the back, and I have someone sitting at the corner of the room at the front, and we toss a ball up in the air, you'll both agree on how it moves. You may not see the same thing, but you agree on how it moves. So there is no preferred origin in the universe, although 3-year-olds think that that origin is where they stand. That's psychology, not physics. Okay, so we've talked about the first law. We've talked about the property of an object that results in that law being effective, and it's called an object that remains at rest because it has substance. It has substance, what we call inertia. It's related to how much stuff is in the object. Protons, neutrons, electrons. Okay? So we use that, for example, by looking at the ratio of the applied force or the net force divided by the acceleration of m. That's how we measure inertial mass. F equals ma. You change F, you change A. You don't change M. But we also can observe that the force of gravity is m gravitational which is mg over m, or the weight, F sub g. Oh, hold on. Let me clean that up just a little bit. I was talking about the F sub g is the product of m times g. So it's the gravitational mass. Now, I've discussed with you, I think, that matter has a lot of different named properties. We have mass, we have charge, we have strangeness, we have lepton number, we have spin up or spin down, which is why there are 2 electrons in every state in chemistry as you fill in the orbitals. You remember that? 2 per level. Okay. Here is something I think you get the Nobel Prize for. We have seen for free fall that the acceleration is down and it's equal to g. Yes? So what that means is mass inertial times A is the force of gravity, which is m gravitational times g. So if bodies accelerate down at a rate of g in free fall, what does that say about those 2 entirely different masses? The first one describes the opposition to motion changes. The second one describes the strength of the force of gravity, of attraction between objects. Those are 2 entirely different things. And yet, the mass that's inertial is equal to the mass that's gravitational. Well, in theory, what I just set up was theoretically I kept them different, but this result says they're the same thing. Think about that. How much one mass attracts another? The Earth attracts you. The Earth's mass attracts your mass. That's called gravity. The second rule, F equals ma, Newton's second law, has nothing to do with gravity, other than when you're dropping. It has to do with acceleration produced by forces. F equals ma applies not just to gravity, but it applies to tensions and normal forces and frictions, all forces. That's okay. So F equals ma is universal. In the context of free fall, where I set that ma equal to mg, since the masses are equivalent, that says the acceleration is g, which means something we talked about back in chapter 2. In the absence of appreciable strength of air drag, all objects fall with the same acceleration. Because these are the same mass, m, falling bodies fall at the same acceleration no matter how much mass they have. the penny and the feather, the hammer and the falcon feather with the Apollo mission to the moon. Gravitational mass is the property of a body that tells us how strong of a gravitational interaction it will have with another mass, such as the Earth and you, or the Earth and the moon. Inertial mass examines how does the motion, the acceleration, vary with respect to the applied force. Any force of any kind. And by looking at free fall, we can see that the property we've observed, that all objects fall with the same acceleration, if friction can be neglected, tells us that those masses are one and the same. So I will from now on say F sub g is mg, and I will say F net equals ma. And I'll no longer worry about gravitational versus inertial. It's related to it. Mass is not weight. This is mass. The whole thing is weight. So, on the Earth's surface, where we have a fairly constant value of g, we can determine the mass of something by measuring its weight. And that's what we do with most things, not all things, but most things. We see how, when we put, like, I don't know, bananas on a scale, the weight of the object of the bananas pushes down on the scale that changes the physical properties of a spring, compresses a spring, or more modern way, it stresses a piezoelectric crystal that happens to have the property that if you squeeze it, it creates a voltage. So the voltage depends upon the squeeze, so you can measure your weight that way. But when you go out into deep space, where the masses that are interacting with you have very, very weak interactions, your weight now is essentially zero. Or if you're in the accelerated reference frame of this space station, where both you and the station are constantly in free fall, which means you're able to go in a circle, you can't weigh yourself. You can't determine your weight in space because there's nothing fixed relative to the Earth because the station's moving. It's accelerating with you. So what am I trying to say? If you buy a box of cookies and it says 1 kilogram, in America, it often will say 2.2 pounds. That is the force in English units equivalent to the weight of 1 kilogram on the Earth. When I take you out into deepest, darkest space, your weight is zero. Right, it's not 2.2 anymore. It's like 1 or something like that. But how about the atoms that make you up? Have I changed that? Have I siphoned off your left arm? No. So your mass is the same no matter where you are. The 1 kilogram is the same no matter where you are. And that's how astronauts weigh themselves. Pardon the gross usage of the term. There's a device that has a seat on it, and the seat is connected to a string, and the astronaut sits in the seat and makes himself as rigid as possible. And then they get pulled to the side and they oscillate. They go back and forth, just like being on a swing set. But the spring's force doesn't care if you're on the Earth or up in a space station. The spring force only depends upon the spring itself. And it turns out, as we'll see near the end of the semester, the period of this oscillation will depend upon your inertia. And so that's how they measure, that's how they weigh themselves in space. They apply a force to them, say a compressed spring, and they see what the resulting acceleration is. So there they're using F equals ma to determine what m is. Have I shown you the balls of different diameter? We don't have a lot of salt spreaders, brine machines. You will see school systems closed a couple of days after a snowstorm or ice storm. And that's because of the properties of frozen water. Frozen water, ice, has a small but not zero coefficient of friction. You can walk across ice. Yeah? But water on top of ice, fluid water on top of frozen water, has an extremely small coefficient of friction. So where we run into issues with our cars or school buses is two things. One is in the early evening and early morning, when the water is not yet frozen or the water is melting on the surface. We have that extreme low friction case, so it's easier to slip. Doesn't require as much force to slip. And the other one is the issue of driving across a road, asphalt, cold asphalt, but that's got a real high coefficient of friction. But then you happen to hit a stretch of road that's a little bit lower or near a ditch, and there's a thin coating of ice, or it's ice that hasn't had a chance to melt because it spends all day in the shade of a tree. So the temperature of the air is not enough to have it melt, and it doesn't get the radiant energy from the sun that causes the other ice to melt. So that's called dark ice, because it's transparent. It's hard to see, and that's where you can get into big problems as well. Why do you think it is that these signs are posted across most bridges that will say something like, caution when there's ice, or it freezes up? I forget how they phrase it, but basically, don't drive across bridges even if the pavement is wet, but not icy. Why does a bridge ice before? Well, yeah, two things. One is it's not insulated on the bottom by ground. And the second thing is the ground is a pretty good heat sink. So it for the most part, keeps the roadbed warmer than the air flowing under an open bridge. It's related to the same issue. It's kind of fun. If you walk around a neighborhood as the snow has begun to melt, you can, on a straight street, compare the insulation quality of the ceiling of your neighbors. The roof that has a lot of snow compared to another one has better insulation, less thermal energy is coming out of the house. So it's not melting the snow as quickly. So they have good insulation, or better, I should say. And there's another thing really neat. You can tell I'm a geek about this. Okay. So last time we were saying just before break that the vector notation employed here implies three separate situations. One for the X, one for the Y, one for the Z, much as we saw for projectile motion. We separated out into components. Yes? Okay, same thing. So all those techniques you worked so hard for test one, they underpin what we're doing with forces. Anyway, so SI unit is a Newton. It's the weight. Huh? Oh, okay, this is just units. Okay. 1 Newton is the weight on Earth of about 100 grams. Okay? But weight is mass times acceleration, so it's kilogram meter per second squared. So, as you see, pound is a unit of force. It's a unit of weight, not mass. In the British system, mass is measured by slugs. Don't ask me what a slug is. Sounds like something boxers do. We talked about gravity. We've talked about gravitational versus inertial mass. So this is, I consider, sort of a miracle. I mean, when you look at subatomic particles, they've got like 20 different properties. Not 20, okay, maybe 10 or 12. So the fact that these two properties are the same, wow. We talked about hugging someone, yes or no? Okay. Newton's third law is the shortest, simplest law you will learn. Newton's third law will be where you perform the lousiest this semester and next semester. Because you have to think about it. It's obvious. It's straightforward. But you have to think about it. So here's what it says. You cannot hug someone without being hugged in return. The baseball bat cannot hit a baseball without the ball hitting the bat. And the force pairs are in opposite directions. Right? The baseball bat directs its force away from home plate. The baseball's force on the bat is directed towards the catcher. Okay? That's what this is saying. Pretty straightforward. But you'll be asked, when a gnat or a small bug hits the windshield of a truck, which one experiences the larger force? The majority of you will say the bug experiences the greater force because it goes kablooey rather than the truck. Well, Newton's third law says what? They're exactly the same force. However, since acceleration is force over mass, you can certainly believe that that bug undergoes an incredibly larger acceleration. So big that it pulls apart and becomes a splat on your windshield. Don't ask me about deceleration now. We talked to you about that, right? That's a word I don't want to get near. It's not in our classroom. Okay? You got me there. Okay. So, if you remember, if not, let's go over it again. F net equals M1A1. Newton's second law. But I attempted to stress to you that this is the net force acting on M1. A body will accelerate due to forces acting on it. Nothing else matters. If the force is not applied to it, it doesn't affect your motion. You are not somehow accelerated across the room because the wall is pushing down with a huge force on the slab beneath us. Doesn't impact you. Likewise, this helps you unlock Newton's third law. F of object A on object B is negative of the force of B on A. So what's the difference between those two forces? Equal and opposite. The first one affects the motion of B. The second one affects the motion of A. And so we reach this I want to say tautology, I guess that's the right word, I don't know, where you have a horse pulling a wagon. And because the harness is a lot like a string, we can say that the force of the horse on the wagon is equal and opposite to the force of the wagon on the horse. Those add up to 0, right? They cancel. So how is it that the horse and cart can move? Pardon? Kind of. You're getting there. But we said the net force was 0. And the answer is one of two answers. One is to say that the horse, okay, it's a weird looking horse. Just not talking about the legs. The horse does experience a force from the wagon on the horse, but the horse also experiences a force of the earth on the horse. It pushes the earth to the left, so the earth pushes the horse to the right. If this force of the earth on the horse is bigger than this force, then the net force is directed to the right. For the wagon, we have the force of the horse on the wagon, and we have the force of the earth on the wagon. You might call it friction, for example, just like the horse's hooves create friction. Now, in that case, for the wagon, hopefully, the wheels are turning. So the force of the earth on the wagon is smaller than the force of the horse on the wagon. That's a tongue twister. Another way to look at it is, this is kind of neat, it's a way to take apart a problem in a more elegant manner. Let's consider the wagon and the horse to be part of the same object, what we call system. Okay, whatever. Okay, it's a unicorn. Okay? In that case, we don't care about the forces between the horse and the wagon. We know that they're going to add up to 0. These are called internal forces. They are entirely within my system box. Sometimes this is shown with a dotted line. When you jump into the air, I do not concern myself about the ligament connections between your small intestine and your abdominal wall. It is of no use to me. They're exerting forces, right? Holding your organs in a certain order. But it's within you. So the wall pulls on your organ pulls on your wall, all that adds up to 0. So as long as I'm describing the motion of you, rather than your small intestine, which would be a little bit awkward, I can ignore those internal forces. And so here we would see in this viewpoint that the force of the earth on the wagon horizontally is smaller than the force of the earth on the horse. And that's why they both accelerate to the right. I believe I mentioned to you earlier, if not, I'll tell you this because it's gross. Your brain floats in a sac inside the skull. Okay? I am told a lot of the brain injury that is created during a crash is not from your head hitting something hard. That's not where the injury occurs. Exactly. The first part of the motion does what? It accelerates you forward if you have a rear-end collision, let's say. Whiplash type of an effect, okay? So your brain is moving forward, your skull is moving forward, the fluid holds the brain from going outside the skull. Life is good. But then when you stop, your head snaps forward, the brain still goes. It has inertia. So what happens in that case, briefer time, it goes into the skull. And the skull contact with the brain is what causes the brain damage. If you have a large enough deceleration, say your chest hits an old-fashioned steering wheel because you thought it would be a good idea to drive a 58 Chevy at 80 miles an hour until you met the tree, it is possible that your heart can be ripped off of the aorta, because that's the main suspension between the heart and the external body, the main aorta. Some really neat stuff happens under extreme conditions, right? Well, yeah, well. Did anybody see the movie The Martian? What happened in the first resupply attempt? Do you remember? This has to do with centripetal motion, which we're about to get into. The boxes of solid food, the thing rotated so much that they became liquefied. And because they were able to flow, like with a tire that has a loose weight on the rim, you get out of balance. Well, getting out of balance for a rotation is a bad idea for a spacecraft. And that's why it got out of control. So, anywho, I'll let you read through that. Oh, that's fun. Okay. So, let's do a problem that we can discuss next time. Let's let this be 20, and let's let this be 70. And let's have a string connected to a mass of, say, m equals 5 kilograms. Find the tensions, FT1, FT2, and FT3, their magnitudes, where FT1 is that string, FT2 is that string, and FT3 is that string. What? That's just the ceiling? I'm sorry. This angle? I'm sorry, that was 70. Well, here we want to pick this apart. So the first part to pick, sounds like Peter Pumpkin, is to look at that system. We want to draw a picture that illustrates all interactions between that mass and the outside world. Since the mass is at rest, we know that what? F net on the mass is 0. Excellent. Well, here's the mass. What are the forces acting on the mass? Oh, sorry. There's a force of gravity of Earth on the mass. And there's the force of the string, which we labeled T3, of the rope on the mass. Every force that you show in a free body diagram for that mass should have either written or thought on M at the end of each force. Yes, sir. Let me make that a little bit more, a lot plainer. Hold on a sec. When I say plainer, I don't mean flatter. Could I what? Yes, it will be. Let's try that again. F net on M equals 0 as it remains at rest. you can either get that A is 0 by the kinematics, right? V squared equals V naught squared plus 2A delta X. Yeah, whatever. Knock yourself out. Or V initial equals V final minus AT. I guess I should put that on the other side. If V initial and V final are the same, then A is 0. Yeah? So we have equilibrium. That's what it's called, equilibrium. So here is my mass M. What are the forces acting on it? Well, I've got this rope attached to it, and ropes only pull, right? And so the force of tension, and we labeled this the third rope, is directed up, and it acts on M. So there's my direction, and there's my magnitude. Notice that that F of rope on M doesn't have an arrow over it. So I'm talking about magnitude. There's also gravity, weight. So we have F sub G is mg of what? Earth on M. And it's directed down. If we are paying close attention to what's happening, that is, the magnitude of a vector, its length is proportionate to its magnitude, you'll notice that those arrows have approximately the same length, as they should. So if I choose, say, up to be positive, I can write that F sub y is 0 equals positive ft3 minus mg. Positive ft3, tension pulls up, minus mg, weight goes down. So this is what tells me that ft3 is equal to the weight of the block. That's almost intuitive, isn't it? If you're suspending something, the spring has to pull up with the weight. Yeah? In fact, that's how we determine the weight often. We have a spring scale. Wrong one. How back do I have to go? There we go. So we have a spring scale. That's a vertical force. Yes, sir. We're trying to figure out what the magnitudes of the tensions are. FT1, FT2, and FT3. So by looking at the hanging mass, I've been able to solve for, let me see there. Yeah, I've been able to solve for FT3. So I know that. Here is the insight you need to use. Where do the three tensions act? On what object do the three tensions each act? They all act on the knot where they are connected. They all act on this teeny tiny mass, go back up, where they're all tied together. Is that mass moving? Nope. So we say not at rest, which says what? F net on the knot equals 0. But notice F net is a vector. Are all the forces horizontal or all the forces vertical? No. It's not accelerating up or down, and it's not accelerating left and right. But those are independent statements. So what we're going to have to solve is the sum of the forces in the x direction on the knot equals 0. Sum of the forces in the y direction on the knot equals 0. I have two unknowns, ft1 and ft2. Mathematics says that to solve for two unknowns, you require two independent relationships. Here they are. The sum in the x direction is 0. Sum in the y direction is 0. Well, how do you take something as lovely as my diagram and make it amenable to applying this idea? We do that which we have always done. Anytime you have a vector and you want to find its components, yeah? Say that's the angle we know. This would be what? The horizontal would be sine or cosine. And this would be ft2 cosine. And what else would I do? Yep. ft1 So again, if we work with a vertical and horizontal axes, we can approach the solution for no net force in the horizontal, and a different requirement that there be no net force in the vertical. Yeah. Aha. Because it is the Chi side. It is the side of the right triangle that is opposite to the angle. Now, in the statement of the problem, I gave you what? I gave you the angle to the horizontal. So what is the angle to the vertical that I used in my example? Theta equals 90 minus 70. Yeah? It matters not that you use 70 or 20. It doesn't matter. Since they are complementary angles, they will have sines and cosines interchanged. So you get the same answer. But when you set up a diagram, which you darn well better, and you label an angle, I expect you to be consistent with the angle on the diagram. So do we have to think and check that? Or do we just go through with our eyes closed? Yeah. Okay. That's part of problem solving. Do I have an answer yet? No. You're going to do this and come back next class and we'll go over the answer to this. If this be the Chi side, then this be the cozy. Or another way to say it, this is the opposite side, and this is the adjacent side. Go Sakatoa. Go suck some toes. Not at all. Let me know when you're happiest. Okay. So again, the recording I'll post will be roughly edited. I'll cut out the part with our break or anywhere where I got away from the microphone, maybe over here. Just makes it shorter, but it'll be a rough transition. And with it, with the audio recording, you've got everything as I do this on the screen. It's capturing both. So my YouTube channel is what? Mary Physics. I forget the rest of the name. I sent it to you in the email, in the announcement. So look on the course website, and it's listed under announcements. Okay? Yes, sir. Anytime you're dealing with forces, you're going to be dealing with Newton's second law. F equals ma. F net. So here's an example of what I find difficult to digest are these symbols. Big T for tension and small n for normal force. It's commonly used, but I'm an uncommon person. And even I don't check my iPod that iPhone that often. I don't check my smartphone that often. Someone. Okay? Okay? Okay. Yum yum. So, what happens if you apply a force to the top of a book? Well, by itself, the book might have what? Good and F sub n. But when you apply another force down, do I change the weight? No. No. The weight is a force between the mass of the book and the earth. Has the earth lost weight? Mass? Has the book lost mass? No. But I have added another force. Remember, we're looking at the key word, net. So, what responds to that? Exactly. F sub n2 is going to be bigger than it was before. So correspondingly, the frictional force would be bigger than before, for example. No, because I could have pushed the book at an angle, right? So the normal force of contact is the push away force of the other surface due to its integrity. That is, it holds together. Excellent. I have an incline. Yeah? And I have a block resting upon the incline. What is the contact force, the normal force, of the incline on the block? I don't know what it is. We can solve that. We will solve that. But I do know its direction. What is the direction of away from the incline? away from the surfaces. That's right, because normal in math is the same as perpendicular. That's exactly right. Yes. No, no. We assume perfect integrity. We assume perfect cohesion of the two materials so they don't intermix. But as a good engineer, we're not going to exceed the load limit. You can study fractures. It's discussed in the text. If you look at a spring under the situation of test, if you look at the applied force, is that right? Hold on a second. Oh, no. Let me change that. If you look at the stretching length, so we're going to stretch the spring out, right? We're going to have a spring and we're going to exert a force to cause it to increase its length by delta x. If I look at the magnitude of the spring force, I don't care about the direction. We know that it's trying to restore. We get something that looks like this, a straight line, where the slope equals the spring constant. Okay? That is the regime of ideal spring behavior. Now, at some point, as those coils start to become distorted, the metal starts to curve more on it bends. That force that the spring gives gets really big for a very small stretch distance, sort of like trying to pull on a straight wire. You're not going to get much change in length as you apply a force, but you will get some change in length. That's the whole idea behind a tuning peg on a piano or a guitar, right? You have a string in the guitar, and what do? You wrap it around a tuning peg. So by turning the peg, you change the length of the original string, right? You stretch it, and that changes the tension, which changes its oscillating properties. So that is the limit when the coils go from this kind of behavior to more like that kind of behavior. And then what happens? Failure. It breaks. So this is ideal. This is too much. Okay? Question, comment? Yes, it does. So what happens just before the rubber band breaks? Does it stretch as much as it did earlier? Mm-mm. It becomes almost rigid, right? Which is why rubber bands kind of stink. They don't work well if they get frozen because the chains can't move past each other like they can when it's at room temperature. So they become more like a string. Yeah. In fact, you can make your own air conditioner with a rubber band. Your lips are sensitive to temperature changes. So here you are. Here's that cute chin you've got, and here's your upper lip. Okay? If you take a rubber band and you stretch it, and you put the rubber band in contact with your lip, you'll say it's warm. By stretching it, you're taking the molecules, chains, and you're extending them, and that requires work. And some of that work is those chains sliding past each other so they release thermal energy. You take the stretched band and allow it to reach room temperature. Then you allow it to shrink to its original length. In order to have the chains be more tangled up than they were when they were stretched, that requires energy. So where does it get the energy from? Environment. So if you put that on your lips, you'll feel it become cold. So the world's smallest refrigerator. I wouldn't count on freezing ice anytime soon, but the temperature does change noticeably. If you use those thick ones like for mail and stuff, that's easier than the thin ones. Okay? Gosh, I love nature. So, this is a stoplight problem similar to what we've been discussing. Rats. Don't pay attention to all that stuff. Okay. Inclined planes. The key thing about any constraint, object has to move horizontally, an object has to move vertically, an object here has to move along that plane. The car can't go straight down. The car can't levitate into the air. So what we need to do is to orient our coordinate system so that one axis is along the acceleration, possible acceleration axis, and the other is perpendicular. So this car can accelerate down or back, depending upon which gear you're in. So that's going to be one of our coordinate axes. That immediately fixes the other axis perpendicular to it. You see that? So then we can draw what's called a free body diagram. FBD. Free body. You can also call it, I guess, a system diagram, where I can take two or more objects, and if I choose, I can consider groups of them at one, and internal forces between them won't affect their motion. So a free body diagram has on it forces. So in the case of the car, my forces are gravity, the normal force. Normal force goes in what direction? Away from the surface perpendicular to it. Yep. And I have friction. Let's assume that the brakes are on so it doesn't slide down the plane. If it were on roller skates, it would go down the plane. So what's the direction of the static friction force? It has to be up the plane. Because I've got the brakes applied. It's just what I've decided. You can work this same problem under the condition that it's accelerating up the plane or down the plane. Do I know the magnitude of the force of static friction? All I know is the limit. Once I'm given mu between the tire and the surface. Because static force of friction is less than or equal to mu sub s, f sub n, and its value is such that the net force equals 0. The friction force opposes the motion between the two surfaces. So it's going to be as big as it needs to be so that it cancels all the other forces. So motion, acceleration, whatever, acceleration is 0. I want you to show acceleration on your diagram, even if it is 0, because you're going to have F equals ma. So here's our coordinate system. Always put one axis in the direction of the assumed acceleration direction and the other perpendicular to it. That makes the math doable. You can choose any other coordinate system you want, but you'll have an A cosine and you'll have an A sine for the other one, and the math becomes a lot hairier. What's the idea? F net equals ma. That's the idea. And we're going to have 0 because it's at rest. Now, do I have to find components of the normal force? Why not? It's directed along the positive y-axis. Do I have to find components for the frictional force? Nope. That's all along the horizontal axis. Do I have to find components for the gravity? Yes. I have to find components for F sub g. And I want them to be components that are along my axes. This is theta, where theta is the angle of incline. So this side is going to be what? Fg times sine of theta. And the other component is going to be F sub g cosine of theta. So now, when I write down in the x direction, exactly. Now, I don't want you to tell me that on a test. I don't want you to tell me that. I want you to respect the process. And it's going to go like this. Let's look at the y direction. F net equals ma sub y, which is 0. And now I use the idea of the sum of the forces in the y direction. So I have F sub n, and it's positive because it's in the direction of my y-axis. I have F sub g cosine theta, and it is negative because it's into the plane, not away from it. Remember, we chose a way to be positive. That's equal to 0. This is what gives us F sub n is Fg cosine theta. 90% of the time, that's what it's going to be. But that's not physics. That's an algebra result. The physics is this relationship. And I want you to show me the physics every time. Because 10% of the time, there'll be other forces. And if they have a vertical component to the plane, they're going to affect what F sub n is. How about the x direction? Along the plane. I'm going to have plus mg sine theta minus force of friction, static, equals 0. So this tells me that to keep the object at rest, my static force of friction has to have a magnitude of mg sine theta. So you could be asked for this problem, does the block slide? So if mu is 0.20 and theta is 45 degrees, does it slide? Well, we have here the requirement for it, don't we? It has to be this big. Yes. They're the same, and I often use them interchangeably. Sorry about that. It's just me being somewhat loose with my terminology. Okay. So let's look at that. Let's look at what that requires. mg sine theta equals the force of friction, and mg cosine theta is the normal force. But what's the force of friction maximum? Mu sub s F sub n. So what do I get? What's sine over cosine? Tangent theta equals mu at maximum theta. That is the angle of, what was the word? Repose. Yeah? That's a pretty neat little result there. That's how we can measure what mu is. Notice the link between the coefficient of friction and the angle at which something begins to slide is independent of the mass. That's because the normal force depends upon mg, and the force that the friction is opposing depends upon mg. So those factors cancel out. So we'll finish this up and we'll continue into chapter 6, which are further problems with forces.
So we're trying to figure out the tension as on the map where they're all tied together.
Mm-hmm.
So
you've got to draw the diagram.
Yeah. So I was just wondering, isn't this 90 minus 70? I don't know. Where did you get that from?
Well, I gave you 70. And, well, you don't have my diagram. Okay. I guess I don't have Jordan. Okay.